Finally, we arrive to our last subtopic for chapter 5, which is capacitor. In this subtopic, you will learn how to determine a capacitor of your structures. First of all, what is capacitor? How to create a capacitor? In practical, a capacitor can be designed by dielectric material sandwiched between two conductors. As you can see in this figure, we have two parallel plate conductors separated by dielectric material. So these two conductors is not touching each other. The capacitor can also be designed by using parallel plate, coaxial, or spherical shape. It depends on the problem or situations. And then the dielectric could be more than one layer. It can be the combination of two dielectric, three dielectric, and so on. For example, I can put one material here, and here is another material. Therefore, the behavior will be different, and you have to analyze the structures by using boundary condition, for example. And the design for capacitors could be parallel or serial. It is as same as resistor. Let's see our parallel plate capacitor. Let's say, is there a positive charge accumulated at one of the surface and another surface have negative charge, so it will create electric field inside our capacitor. You have to remember, inside our capacitor is dielectric material. Even though there is no conduction current, however, the electric field exists. Well, conduction current is well known as a DC current, direct current. So for the conduction current, it will see the capacitor as an open circuit because the conductor is not connecting each other. It is separated by dielectric. We know that dielectric cannot conduct DC currents. However, for time varying field, we will see later on there is a current inside our capacitor. We call as a displacement current. When we have electric field inside our capacitor, there will be the potential across the capacitor, which is in this case VAB. If we want to determine the value of capacitor, is basically equal the magnitude of charge. Normally we take at the positive charge and then divide by the potential across the capacitor. So Q divided by VAB. Since capacitor equal to Q divided by V, we know that Q is equal to rho S ds, and our V is equal to E dot dl. And then we can further expand the rho S to be dn. So inside our capacitor, there will be the D field, which is dn, normal to the surface, and we have this is a unit vector of D. For the case of the spherical capacitor or cylindrical capacitor, so the vector normal is always in all directions. because the surface is normal to all directions. We know that capacitor can store energy. So to determine the energy stored by the capacitor, we can use this formula. W equal to 1 over 2 Q VAB, and we can further expand the Q into C VAB, and finally we can get this expression, energy equal to 1 over 2 C VAB squared. So to use either this expression or this expression is depend on what information you have from your questions. So this is our VAB across the capacitor, and this is the direction of DN. Let's see an example related to capacitor. The question is, a very long coaxial cable of length L as shown below has epsilon equal to epsilon naught epsilon R between A and B, which means here is a dielectric material. Other region is epsilon equal to epsilon naught, which is a vacuum of space. If a charge Q is placed at R equal to A, while negative Q is placed at R equal to B, find A, a capacitance of coaxial cable, and B, electrostatic energy stored in the capacitor. So, to solve this problem, first, we want to find what is the capacitance of the coaxial cable. To find the capacitance, we have to do the reverse engineering. Our aim is to find capacitor C, where the capacitor is equal to Q divided by VAB. Before that, we have to determine what is the potential difference between A and B, which is VAB equal to minus B to A E dot dl. We want to find VAB here. So to find VAB, we have to use E field. On the other hand, total charge on surface A, we have to determine, which is Q equal to rho S ds, or rho SS for uniform surface. And the charge density in this case is equal to D dot N. And to find the electric field intensity, we use the Gauss law. So the Gauss law said that the closed integration of epsilon E dot ds equal to Q n close. So you have to remember how to find the E field using Gauss law. So now we have to solve from down to upward. Okay. Let's go back to our structures. Okay, I draw a Gaussian surface inside our dielectric material, and then I can find what is the E field or D field in that region between A and B. By using epsilon E dot ds equal to Q n close, alright, for long coaxial, we know that the surface area ds is equal to 2 pi rl for the left hand side. Since we have epsilon here at the left hand side, so we bring the epsilon to the right hand side, so basically it becomes Q divided by epsilon r epsilon naught. So we can determine E equal to Q divided by 2 pi epsilon r epsilon naught rl in the direction of r voltmeter. So I not go into detail about the Gauss law. I assume that you already know how to determine the E field using Gauss law. Next, to find the D field, since D equal to epsilon E, so we can multiply the E field with the epsilon, which is epsilon R epsilon naught. So our D field equal to Q divided by 2 pi Rn in direction of R coulomb per meter square. So we can use our D to find what is the charge density rho S. So rho S equal to D dot N or equal to Q divided by 2 pi AL in direction of R dot product with R. Okay, why A? Because we want to find what is the rho S at R equal to A. So we change our R here to be A. So our rho S is equal to Q divided by 2 pi AL coulomb per meter square. So this is a note that rho S is at R equal to A and the vector normal is equal to R. So you can also use rho S equal to Q divided by S, because this is a uniform surface. When we know E, so we can determine what is a VAB by using negative B to A E dot dl. So we replace E into Q divided by 2 pi epsilon R epsilon naught RL in the direction of R, and our dl is equal to dr in the direction of R. So by solving these equations, so finally we got Q divided by negative Q divided by 2 pi epsilon R epsilon naught L ln A over B. Or we can make it to be positive, which is Q divided by 2 pi epsilon R epsilon naught L ln B over A volt. Finally, we can determine the capacitance because we know what is Q, what is VAB. In this case, actually, you don't need to determine Q because it's given that the total charge on that surface is Q. But in the case of you are not given Q, so we have to determine what is the value of Q. So here, C equal to Q divided by VAB. So Q divided by Q divided by 2 pi epsilon R epsilon naught L ln B over A. So we can cancel Q here. So we can see that our capacitance is equal to 2 pi epsilon R epsilon naught L divided by ln B over A, and the unit is farad. From the solution, it is clearly shown that our capacitance value is independent with the charge or potential or whatever electrical parameter. The capacitor is only depend on the physical behavior of your capacitor, which is the length, the radius, and also the material properties, which is epsilon. Next, to determine the electrostatic energy stored in the capacitor. W equal to 1 over 2 QAVAB. We know Q, we know VAB. So you just put inside our formula. So finally, we can obtain the energy equal to Q squared divided by 4 pi epsilon R epsilon naught L ln B over A, and the unit is joule. From this expression, we can see that the energy stored depends on the charge. So more charge means more energy will be stored. However, capacitor have its limits.